Okay, Matt Roscoe here with continuation, part 2 of our lecture on chapter 13-1 on polyhedra. So the last piece I want to talk to you about is about these special polyhedra. They're, what we call the regular polyhedra or Platonic solids. So a regular polyhedron, or more commonly called a Platonic solid, is a convex polyhedron whose faces are congruent regular polygons constructed such that the number of edges meeting at each vertex is the same for any vertex. So these are them. It turns out that there are only 5 of these. And let's just make sure that you understand the difference between these and sort of other solids. These are more restrictive in the sense that the faces have to be regular polygons. So remember that a regular polygon is a polygon whose edges are all the same size or same length, and whose angles are all the same measure. So, for example, on this one on the left, which we call a tetrahedron, the faces are all equilateral triangles, and of course, if they're all equilateral triangles, they have equal edge lengths and equal angles. The angles in between edges would be 60. Whereas this one, the cube, the one we're most familiar with probably in our day-to-day interactions with these solids, this one, of course, the faces are all squares, so edges are all equal length and the angles are all 90. So the one here we have, which is called an octahedron, here the edge lengths are, the faces are all equilateral triangles. We do have one that's made with regular pentagons. This one's called the dodecahedron here. And then the last one is called the icosahedron, and it's built again with equilateral triangles. And if you've ever played Dungeons and Dragons, you'll recognize that these are the set of dice that make up the dice for Dungeons and Dragons. And they are the only, I guess, regularly sided dice that are available in the solids. In other words, they're the only ones whose faces are all exactly the same in terms of being regular polygons. Now, I don't know if this sort of gives you a little bit of pause, but I don't know, maybe I'll show you really quick. I do have some models of these already constructed just to give you a better sense. But so this one right here would be the icosahedron. It's built out of equilateral triangles. If we were meeting live in non-pandemic times, I'd actually ask you all to build these. But there it is, the icosahedron built with equilateral triangles. And notice that the number of triangles that come together at a point here are 1, 2, 3, 4, and 5, right? So 5 triangles come together at a point. So that's what makes it different than the tetrahedron. The tetrahedron, of course, is built with the same objects, that is equilateral triangles. But the difference is that this one has 5 equilateral triangles that come together at a point, and this one only has 3 equilateral triangles that come together at each point, as you can see. And then, of course, the octahedron, which is also built out of triangles, has 1, 2, 3, 4 that come together in a point. So you can kind of see these as sort of in progression, 3, 4, and 5 triangles coming together at a point for the tetrahedron. The octahedron, we call it octahedron because of 8 sides, and the icosahedron, and we'll talk about the sides on that one in a bit. So those 3 are made with triangles. Interestingly, only one of them is made with squares, and it's the cube, and the cube only has 3 squares that come together at a point, and then only one of them can be made using regular pentagons, and again, like the cube, 3 come together at a point, but we get much more sides than we do with the cube here. This is the dodecahedron. Dodeca, 2, 10, so it turns out it has 12 sides. So if you're a Dungeons and Dragons player, you recognize this one as the 4-sided die, this one is the 6-sided die, this one is the 8-sided die, this one is the 12-sided die, and this one is the 20-sided die. So the icosahedron has 20 faces. But this is somewhat strange, right? There are an infinite number of regular polygons. We have a regular polygon with 3 sides, with 4 sides, with 5 sides, with 6 sides, 7 sides, 8 sides. We could have 9, 10, 11, 12, up to as many sides as we want. And the thing gets closer and closer, of course, to a circle with the more sides we add to it. But big question is, why are there just 5 Platonic solids? So I'd like to address that really quickly and talk about, give you a brief proof sketch of why only 5 of these exist. Because it has been quite a source of curiosity to mathematicians across the centuries. These have been intensely studied, and in fact, the Platonic solids turn out to be, the fact that there were just 5 of them led early, scientists or philosophers to theorize about what this meant for our universe. And Plato thought that these were representative of the early theory of elements, and that each one of these corresponded to one of the primitive elements, or what we think of as the early elements. So the tetrahedron was associated with fire, the cube was earth, I think the octahedron was water, and I think the icosahedron was wind, I believe. So this idea that just 5, that must mean something about sort of our world, and really, these solids have something to do in terms of getting us to start thinking about the world's smallest parts and pieces. So in a sense, they spurred a search for what eventually became the atomic theory of how our world is built out of these small parts and pieces, or elements. But let's go back to our question here. We've got an infinite number of regular polygons in the plane, but only 5 regular polyhedra in 3-dimensional space. So why does that happen? Let's go ahead and talk that over just a little bit and see if we can give you a rough idea of why that happens. So the place to start here turns out to be with the regular polygons. So if I think about regular polygons, these are going to become sort of the faces, right, of our regular polyhedra. And so it might be interesting for us to think about what can we build with regular polygons. We know that if we have sides of length, if we have 3 sides, then the regular polygon is an equilateral triangle, and its edge, its angle is 60. If we have a regular polygon of 4 sides, then we get a 90-degree angle. And the question is, what happens with 5 sides? Well, one way to sort of think about this is if we want to know what all of these angles are, we could build some sort of a formula. And the formula that we could build would depend on how many triangles we can draw inside each one of these. And it looks like I can draw a single triangle inside a triangle, 2 triangles inside a quadrilateral, 3 triangles inside a pentagon, and it looks like we're going to get 4 triangles inside a hexagon, and we're going to get 5 triangles inside a septagon. 1, 2, 3, 4, 5. So I would assume we're going to get 6 inside the octagon. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So it seems like if n is the number of sides, then we get 2 less triangles than this number of sides. So n minus 2 is going to be equal to the number of triangles on interior. And then each triangle is 180 degrees of angle sum. So a formula for the interior angle of a regular polygon, so angle measure, regular polygon, is going to be equal to the number of triangles that we get for each one, which is n minus 2, times 180, which will tell us the total of the angle. But if we want just one of those angles, we have to divide by how many angles there are, which is just n itself. And so this would give us some sort of a formula that would tell us the angle measure for a regular polygon that has n sides. So let's just check it. Let's see if we call it angle sub n equals 180 times n minus 2 all over n. Well, if I have, let's say, a 5-sided, well, let's do the 4-sided just to see if it works. We get 180 times 4 minus 2 all over 4. So that's 180 times 2, which is 360, divided by 4 is 90. So it definitely predicts the 90-degree angle for a 4-sided figure, regular polygon. But let's see what it says for a 5-sided polygon. Here we get 180 times 5 minus 2 all over 5. So 180 times 3 divided by 5. So 3/5 of 180. 3 divided by 5 times 180. We get 108 for our angle measure here. So this particular angle here is 108 degrees. And for 6, what we're going to get, angle measure for the 6-sided figure will be 180 times 6 minus 2 all over 6. So 180 times 4 divided by 6, that's 120. So this one is going to have an angle measure of 120. And of course we could keep going. This is going to continue to grow, right, and get larger. Let's just do 7 and 8 really quick on our calculator. So 7 would be 180 times 5 divided by 7. So this is about a funny number. This is 128.57 degrees. It's really a strange one because, of course, we're dividing by 7, which doesn't work out so well. Let's see about the 8-sided. That would be 180 times 6 divided by 8. So it turns out that this angle here is 135, which was a problem on one of your assessments recently. But the reason I do this is because it gives us some insight into what we can build. Let's start with triangles. If we start with triangles and we put them vertex to vertex in such a fashion, then we certainly could put 3 triangles together at a vertex. That would look like this, right? If I put 3 triangles together at a vertex, then I can form a vertex out of 3 triangles. And the reason I can do that is because each one of these angles is 60 degrees, right? So that leaves me some extra space here, which allows me to fold this thing up. So it turns out that if I choose 3 to a vertex, I get the tetrahedron, which is what I'm about to build here. So in other words, 3 to a vertex leads to the construction of this guy. I could put 4 to a vertex. If I do that, then I get that figure. Well, then I've got to build 4 to a vertex here, here, and here, but it's certainly possible, and that will lead to this figure, which is the octahedron. And then the last thing I could do is another thing I could do is I could put 5 to a vertex right here, and then I would be able to fold that guy up. And 5 to a vertex is going to eventually lead to the construction of this guy, which is the icosahedron. Now the big question would be, can I put 6 to a vertex? In other words, can I put one more in there? And the answer is no, and the reason is because that number right there, right? If I put 6 to a vertex, then I have 6 times 60, or 360, and this thing lies flat. And if it lies flat, there's no, what we call a defect, there's no space to allow me to fold this thing up and to create volume inside of it, and it's to create kind of like a cup, right? So if the thing's flat, I can't fold up and create volume. So in other words, it's only 2-dimensional if I add another triangle. So what it turns out that, if I'm building something with these equilateral triangles, I can choose 3, I can choose 4, or I can choose 5, but I can't choose 6 or above. And 3, 4, and 5 choices lead to the tetrahedron, to the octahedron, and to the icosahedron, right? So I can build with those. I can build in that fashion, but no further with equilateral triangles. I hope that makes sense for those 3. Now, the next thing to take a look at is what can I do with squares? Well, I can't just choose 2 to a side, because if I choose 2 to a side, then folding up, all I get is this, right? I have to have at least 3 to a side. To a vertex is what I should be saying. So if I choose 3 to a vertex, in other words, 3 squares meet at a vertex, then I do indeed have space to fold this thing up and create some sort of a cup. that will hold volume, and that leads to the creation of the cube, right? But really similar to the equilateral triangle case, I can't choose 4 to a vertex, because if I put a 4th triangle in there at that spot, this thing will lay flat. The reason it will lay flat is because 4 of these angles are 90, and 4 times 90 is 360. So I'll have no defect to fold up to actually be able to create anything. So in other words, I can choose 3 squares meeting at a vertex and no other, because there won't be any space to build up. Hope that makes sense. So the only thing you can build with squares is a cube. Now, the very last one to take a look at, or the next one to take a look at, is this one, and that is the building with pentagons. And when I build with pentagons, I can indeed put 3 to a vertex. This is what it looks like, and you can kind of see why this works. If the angle at the vertex is 108, and this is 108, 108, and 108, 3 108s gives us 324 degrees, and that leaves a little slice in here that allows me to go ahead and fold up to create some sort of a cup. And that becomes the first sort of look at a vertex of a regular polyhedra that ends up, if I continue to build 3 to a vertex, ends up looking like this big guy here, the dodecahedron. But you can see that right away, I'm not going to be able to shove another one of these pentagons in there to build 4 to a vertex. So 3 to a vertex is all we get, and that's the end. And then the big question then becomes, what about everything else? And you can see that everything else is going to have a problem. And the reason is that if I choose to build with hexagons, I need at least 3 to a vertex. I can't have 2. And if I put 3 hexagons down, vertex to vertex, 120, 120, 120 is 360, and it lies flat. And there is no space to fold it up. And of course, that will disallow building with a hexagon at all. And of course, since these angles continue to grow in size, if I put 3 to a vertex together here, they're actually going to overlap. And so I won't be able to fold up at all because of the overlapping. And the same would be true with octagons, nonagons, decagons, and so on. So in other words, the only ones that work are these 3, and the reason they work is because you can put 3 to a vertex together and the 3 angles sum to less than 360. In the case of the triangle, I can also put 4 to a vertex and 5 to a vertex. So I actually get three potential builds out of the triangle, only 1 out of the square and out of the regular pentagon. So I hope that gives you just some sense of why there's only 5. I think it's a kind of an interesting, I guess, constructive proof that this only works when we have enough space to sort of fold the figure up. So one thing I did want to make you aware of is there's this really cool site out there. If you just if you go ahead and type in Polyhedra Explorer, Polyhedra Explorer, or Polyhedra Viewer will even be better, but what you're looking for is this Polyhedra Viewer, which is at tessera.li, and you'll get a picture that looks like this when you first get there. And this is over 120 different solids that are presented here that can be transformed, but right at the top of the list, of course, are the Platonic solids, which are these 5. You can see the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. So if you want to play with these, this is a great site to take a look at. Let's take a look at the dodecahedron, for example. So here's the dodecahedron. You can just grab and move it. You can also zoom in and zoom out, and it's kind of a nice app. You can actually see through it fairly well to see edges on the other side. It's well lit, and there are some really nice things to play with over here that I'll get to in a bit. But I think it's the best site I've seen for getting to play with these without actually having one in your hand. Let's take a look at the octahedron. So the octahedron, of course, looks like this. Let's take a look at the, I don't know, let's say the icosahedron. The icosahedron looks like this. Okay, so you have a place now that you can go to play with these, at least virtually. Let's take some time now to investigate these 5 solids. So would you make this table up in your notes and then use the polyhedra viewer that I just showed you to try to determine how many edges, vertices, and faces there are. So maybe I should go through with the cube to talk about it first, just to give you a sense of what I'm after, and then we'll take some time for you to do this on your own and come back and see what we get. So if I go to the cube, here it is. So I'm trying to determine how many edges, vertices, and faces there are. Well, from interacting with a die, you probably know there are 6 faces. But let's see how many edges will there be. So an edge is just one of these lines that connects a vertex to a vertex, and the question is how many of those are there. There are 4 edges to this face, and there are 4 to the bottom. So 1, 2, 3, 4 down there on the bottom, and then there are 4 along the sides, 1, 2, 3, 4. So it looks like there are 12 edges to the cube, 6 faces, 12 edges. And then the question is how many vertices are there, and vertices are where the edges come together. So in other words, this thing right here would be a vertex, and there are 1, 2, 3, 4 vertices on this side, and of course 4 on that side down below out of sight. So it looks like there are 8 vertices. So 8 vertices, 6 faces, 12 edges for the cube. Would you go ahead then, go ahead and pause the video right now and fill in the rest of this table using edges, vertices, and faces. And then what I'm really curious to see is if you notice anything special about these numbers, and we'll discuss that once you come back with your table filled in. So go ahead and pause the video right now, and we'll talk about this in just a second. Okay, well, I'm back now, so let's go ahead and talk about what you got, and hopefully you got something similar to me. So the hardest ones, of course, to count are the 2 more complicated Platonic solids, which are, of course, the dodecahedron and the icosahedron. And I'll just talk to you a little bit about how I counted the dodecahedron. So the way I counted the dodecahedron is I first recognized that there are there's 12 faces here, right? Because you have 5 here, 5 around the outside, I guess here, and plus this one, so 6, and that's 6 faces in view and 6 faces out of view. So dodeca, 12 faces. So then when I thought about doing the edges, what I said is, well, each face has 5 edges associated with it, right? So if I take a face and I multiply it by 5, I get the number of edges, but got to be careful because each edge is shared by 2 faces, right? So if I take 12, multiply by 5, I get 60, so 60 edges, but each of those has been counted twice, right? So I need to divide that by 2 because each edge is shared by 2 faces. So I take the 12 times 5, divided by 2, I get 30 for the number of edges. And a similar thing, you can think similarly for vertices. You can say, well, each face, of which there are 12, has 5 vertices, so again 60, but each vertex is shared by 3 faces. Do you see that? So this vertex, for example, right here, is shared by those 3 faces. So I need to take that 60 and divide by 3, which will allow me to calculate that there are 20 vertices here. So just to give you a sense of what I'm getting, this is what I'm getting for my counts. The tetrahedron has 4 vertices, 6 edges, and 4 faces. The cube, 8 vertices, 12 edges, and 6 faces. The octahedron, 6 vertices, 12 edges, and 8 faces. The dodecahedron, 20 vertices, 30 edges, 12 faces, whereas the icosahedron has 12 vertices, 30 edges, and 20 faces. And I don't know if you've noticed anything happening here, but it does seem like there are some consistency between all of these, I guess, terms, that when we add the vertex plus faces, we get something that's really close to the number of edges. In fact, it's always 2 more than the number of edges. So 20 plus 12 is 32, that's 2 more than 30. 6 plus 8 is 14, that's 2 more than 12. 8 plus 6, 14, 2 more than 12. 4 plus 4, 8, which is 2 more than 6. So what it seems like happens is what we get is we have this relationship that says vertices plus faces is going to be equal to the edges plus 2 more, right? And this is a very famous formula called the Euler characteristic. And it turns out that it's true for all polyhedra, not just the Platonic solids. Any sort of polyhedra that you build, so long as it doesn't have any holes in it or any faces where sort of something is constructed on top of a face, or a protrusion on that face. So as long as it's a polyhedra, no holes, and no, I guess, extrusions on faces, then we have this relationship, which is kind of neat relationship. I've seen this show up in middle school textbooks, and sometimes kids are asked to solve, for example, for edges if they know vertices and faces, or faces if they know vertices and edges, and whatnot. So it's a nice algebraic, simple algebraic relationship too, where kids can kind of connect geometry to algebra. So be aware that that is a result, and it's actually true for all polyhedra. The other thing I wanted to draw your attention to, and hopefully you saw this, and if we were live, I'd ask if anybody saw this, but it does seem like these things come in pairs, right? These guys, they're almost like rearrangements of each other's data, right? I mean, the edges stay the same, but the faces are swapped for vertices. That's kind of interesting, and it actually has a really deep and meaningful representation. And what is kind of neat here is that the 12 goes to 12 here, and the 20 goes to 20 here, the 8 goes to 8 here, the 6 goes to 6 here. Edges stay the same, and of course this one stands alone because if we did swap vertices and faces, it would just be itself. So it seems like this one sort of belongs to itself, whereas the 2 pinks belong together and the 2 oranges belong together. So in other words, the cube and the octahedron must have some really, important relationship to each other geometrically, as must the dodecahedron and the icosahedron, and the tetrahedron must have that relationship, to itself. And it's neat that the app that the site that I sent you to, again, this is just the Polyhedra viewer, allows you to see this. I think it's easiest to see it if we take the cube first. And it turns out that this relationship is called a dual. And what a dual means is if I swap faces for vertices. So for example, imagine building something inside this cube where on each face, at the very middle of the face, I created a vertex. In other words, I place a point here, a point there, and a point there, and a point on all 6 faces, and then I connect all those points. What would that thing look like? And to see what that looks like, hit dual here, and you'll see that it will look like that. In other words, if I build this, swap faces for vertices, then what I get is the octahedron. If I hit the dual again, if I swap that vertex for a face, I get back to the cube. What's fascinating to me is that the number of edges doesn't change here. Just the faces and vertices swap. So I don't know if you find that interesting. I certainly do. I think it's really cool. And of course, now that you've seen it with the cube, let's take a look at what it looks like. So the cube and the octahedron are duals of one another, and it turns out the dodecahedron and icosahedron are duals of one another as well. And that's the dual relationship that you can see in vertices, edges, and faces, where we literally just swap the number of vertexes for the number of faces in each figure. So that's kind of neat. And the one, of course, that's remaining to see is the tetrahedron, which, again, if we place a little point on each one of these faces and connected them, you can imagine it's going to be another tetrahedron. So there you go, dual, dual. Tetrahedron is its own dual, so it's kind of like its own inverse. And really that's about so just once again, tetrahedron's dual is itself. Cube's dual is the octahedron. And the dodecahedron's dual is the icosahedron. And all we're doing here is we're creating a vertex where there once was a face, and swapping basically vertices for faces for each of these. So just to conclude, the number of vertices, edges, and faces for any polyhedra can be related by vertex plus faces equals edges plus 2. In the case of the Platonic solids, they come kind of in pairs that can be related by this dual relationships. And yes, just to close, my last slide is, of course, this Euler's formula: vertices plus faces, I had to say minus edges equals 2. And of course, that's vertices plus faces equals edges plus 2 as well. And that's it for today. Good luck on your homework, and I look forward to seeing you when I get back on Friday.